Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 9 of a unit Oscillations. So let's begin with today's class. In today's session we are going to discuss about the damped simple harmonic motion. Let's begin. What is damped SHM? When we say it's a damped oscillation, that means a periodic oscillations with gradually decreasing amplitude are known as the damped harmonic oscillations. And in this situation, energy is lost due to negative work done by the damping force. And this damping force may arise. This damping force may arise due to the friction between the moving particles and air resistance, or it could be due to several other reasons. So in this in the presence of this kind of damping force, the amplitude of the SHM goes on decreasing, and this kind of oscillations, that is what we call as the damped oscillation. Now let's look how this oscillations will work. That, as you can see, that is simple pendulum, and this simple pendulum has been put up into the certain medium, and this medium is having certain damping constant. So it's a considered a bob that has been tied with a string and oscillating on its mean position. And this, because of its damping force of this medium, this bob will stop oscillating after some time, and this is what we call as a damped oscillations. Now let's look at the situation. That this could be the situation that what we have done is, this is one of the rigid support, and with this rigid support we have connected one of the spring, and with this spring a block and a vane system has been connected, and this has been put up into the container, which is filled with certain liquid. As when we displace it once, it will start oscillating upward and downward. Yes, but this is oscillating into a liquid, and as you understand very clearly that this liquid, or suppose this is the water, then it will opposes the motion of the vane, and at sooner or later this will oppose the motion of a block, and this block will stop itself. I hope this is clear. So these are the cases of the damped oscillations. And let's discuss certain about the damping force. This damping force is arises because of the gravitational pull, because of the air resistance, or we can say it is because of friction between moving parts. Yes, so this damping force is directly proportional to the velocity of the vane and the block, and this could be given as this Fd. This damping force is directly proportional to the V, and when it is directly proportional to the V, if I remove the proportionality constant, I need to add one more constant, and this is B into V, where V is the damping constant. And the negative sign indicates that this damping force tries to oppose the motion. Yes, so the situation is total force on the block would be equals to damping force plus restoring force that is provided by the spring. So we know that this total force on the block, it's an F is equals to ma, that is equals to damping force, it's an Fd, plus spring force, it's an Fs. So this is equals to ma is equals to minus of bv plus minus of kx, and it's an ma plus bv plus kx, that is equals to 0. If I write it's an m into a, that could be written as m into d square x by dt square, plus b into v, which is b into dx by dt, plus k into x, this is equals to 0. I hope this is clear. So this could be also written as, this is d square x by dt square plus b by m into dx by dt plus k by m into x, this is equals to 0. And this represents an oscillation but this is the oscillation of decreasing amplitude. So this could be given as it's an A dash cos omega dash t plus phi, something like this. And this A dash represents an amplitude of it represents the decreasing amplitudes. So in this situation, motion of the block under the influence of the damped force, on solving the equation that I have written, we get it's an x is equals to a into e to the power minus of bt by 2m into cos omega dash t plus phi. This is the amplitude, so I can write it's an amplitude is equals to a naught into e to the power minus of bt by 2m, where b is the damping constant and rest of the term you know. So this is the decreasing amplitude, that is what we get. And this is the situation, it's an a into e to the power minus of bt by 2m is the amplitude of the damped harmonic oscillations, and this amplitude decreases with the time exponentially. And the next is the angular frequency, which is equals to omega dash, and this omega dash could be given as under root of k by m minus of b by 2m whole square. If I want to find out the time period of oscillation, then this could be given as t is equals to 2 pi under root of k by m minus of b by 2m whole square. Yes, so the period of oscillation increases. Period of oscillation increases due to the presence of minus of b by 2m, as this term is subtracting. This is going to increasing, and thus damping increases the period, and as period increases, that means amplitude decreases. If I plot the displacement versus time graph, it is something like this. That look at this, initially the amplitude is this much. After certain time passes, this amplitude becomes this much only. Yes, so I hope you understand the effect of this. Yes, initially amplitude was this much, and by the time passes, it will come on decreasing and something like that. Yes, so it will goes on decreasing, and at certain instant of time, probably it could take a very longer time. That depends on the damping force, but sooner or later it is going to stop, that is for sure. I hope you understand this. Have you got this? Have you? Now, do you have any doubts up till now? Is there anything? Is there? No? Great. Now let's look at certain quick questions. The question says it's a periodic oscillations of gradually blank are called as the damped harmonic oscillations. Yes, they are the oscillations of decreasing amplitude. Next, the damping force depends on, basically the damping force is directly proportional to the minus of V, and this could be minus of B into V. The nature of the surrounding, the damping force depends on the nature of the surrounding medium. It depends on the frequency, it depends on the amplitude, it depends on the wavelength. No, so damping force depends upon this, it depends on the nature of the surrounding medium. Next, damping force Fd is given by, yes, it's a minus of B into V. Next, when damping increases, its time period increases, and as time period increases, amplitude decreases. I hope this is clear. So what we understood from this is A is equals to A naught into e to the power minus of bt by 2m. This is the new amplitude, or amplitude of the decreasing, it's an oscillations of decreasing amplitudes. So not only amplitude, even total energy is going to decrease. How? Let's have a look. The total energy, what we call, is the half k into a square. And if I make this as an half into k into a square, then this is simply a naught square into e to the power minus of bt by 2m whole square. So this is simply is equals to half k a naught square into e to the power minus of 2bt by 2m. This has gone, and this is simply This is simply half k into a naught square. This is the e naught into e to the power minus of bt by m. This is the e. I hope this is clear. So this e will be equals to e naught into e to the power minus of bt by m. This is the energy what we understood. This is the energy. E is equals to e naught into e to the power minus of bt by m. I hope this is clear. Is it clear? Is it clear? Great. So are you ready for one of the questions based on this? Let's say the question says that if amplitude of damping oscillations, if amplitude of damping oscillations becomes 1 by 2, it's in half of the initial amplitude, after 25 oscillations, what will be the amplitude after 50 oscillations? This is the question. How do we do this? What can be done? So my master formula says it's an a is equals to a naught into e to the power minus of bt by 2m, and according to the data, amplitude becomes 1 by 2 of the initial. This is the initial, so this is a naught by 2 is equals to a naught into e to the power minus of b into t by 2m. So let's consider t is time period for one oscillation. Then this t is equals to, for 25 oscillation, it's a time taken, it's a t is equals to 25 into t. So the situation is sorry, this is equals to a naught by 2, which is equals to a naught into e to the power minus of b into 25t divided by 2m. And if I'm supposed to solve this and this has gone, this is equals to 1 by 2 is equals to e to the power minus of b into 25t divided by 2m. So this is 2 to the power minus of 1, which is equals to e to the power minus of b into 25t divided by 2m. So this is plus, and this is the value of e to the power b into 25t divided by 2m, that is equals to 2. I hope this is clear. Is it? Great. Now what I want the amplitude after 50 oscillations. So it's an a is equals to a naught into e to the power minus of bt by 2m. This is equals to a naught into e to the power minus of b. 50 oscillations, each oscillations take t time, so 50 oscillations will take 50 into t time, divide by 2m. This is a. So this is equals to a naught into e to the power minus of b into, look at this very carefully, I will take this as 25t by 2m whole square. I hope this is clear. Yes. Why I am going to write this? Because e to the power minus of b into 25t by 2m, it is having the value of 1 by 2 that I am having it. So I can simply write this, it's an a naught into 1 by 2 whole square. This is tends to a naught by 4. I hope this is clear, and you can do this with this kind of technique. Is it clear? Is it? So will you able to solve this kind of questions? Will you? Now let's have one of the question that is, try yourself, you are going to attempt it. If initial energy is E naught, and energy is 1/4 of the original after 20 oscillations. Find out find out energy after 60 oscillations. Yes, this is try yourself. You are going to attempt this. Yes, you can take a reference from the previous question, and that will definitely help you to do this. I hope this is clear. Is it? Great. Now let's discuss the next. It's a forced oscillations and condition of resonance. So let's discuss first what forced oscillation is. So forced oscillation, we can say when a body oscillates under the influence of an external periodic force, not with its own natural frequency but with the frequency of the external periodic force, its oscillations are said to be forced oscillation. You can see this that we have apply a certain resonance, or we can say we have apply a certain vibration, certain external effort to this tuning fork. It's a tuning fork 1, and as this is vibrating, this is vibrating due to this force. So this is not vibrating on its own, but the second tuning fork vibrates automatically when the first fork is given certain vibration. So this is what we understand, or this is what we call as the forced oscillations. Yes, that they are not going to have its oscillation on its natural frequency, or we can say on natural time period, but they are going to oscillate due to the driven frequency. I hope this is clear. Yes, great. Next, let's suppose the certain examples are that the stem of a tuning fork is pressed against a table, and as it is pressed against the table, then the vibrations has been passed on to the second tuning fork. And if the vibration has been passed on to the second tuning fork, it will start vibrating, and due to this vibrations, it will oscillate, and this is what we call as the forced oscillations. The soundboards of all stringed musical instruments like sitar, violin, etc., this all are have the forced oscillation. So suppose an external force F of amplitude F naught that varies periodically with time is applied to a damped oscillator, and such a force can be represented as that this is F is equals to F naught cos omega t, and the force frequency, sometimes we also call this as a driven frequency. This driven frequency is what we call as an omega t. Yes, so the motion of a particle under the combined action of linear restoring force and this damping force, which is a time dependent, is represented by this total force. It's an ma. Now another force, it's the restoring force, it's a minus of kx. Damping force, it's a minus of bv, and this additional force which is equals to F naught cos omega dt. So this is equals to m into d square x by dt square plus b into dx by dt plus kx, that is equals to F naught cos omega dt. And after the natural oscillations die out, the displacement could be written as xt is equals to a cos omega dt. As you can see, this is the driven frequency with which it oscillates, plus phi is the initial phase difference. So from this its amplitude can be calculated as such, like this. This is the amplitude, that a is equals to F naught upon m square, into bracket omega square minus omega d square. It is something like this. This is omega d square whole square plus omega square into b into d whole square. This is the amplitude. This is the amplitude of the forced oscillations. I hope this is clear. Is it clear? Great. So we could have two cases. In a case 1, if it's an m into omega square minus of omega d square is greater than omega d into b, then this amplitude could be given as equals to f naught divide by, this is going to be cancelled out because this is the smaller term, so I'm going to write this as an m into omega square minus of omega d square. Yes, the square has been removed because this is the square root of this. As this was the first case, let's check it out the case 2, and for the case 2 let's consider the reverse condition, and that is that if omega d into b, if omega d into b is greater than, this is greater than m into bracket omega square minus of omega d square, then amplitude a could be written as a is equals to f naught divide by omega d into b. This is the amplitude. I hope this is clear. As you can see that case 2 is having a larger amplitude as compared to the case 1, and it depends on the damping constant. So sooner you will decrease the damping constant, you will have a larger amplitudes. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's discuss a very special case of this forced oscillations, and this is the case of the resonance. So it is a particular case of forced oscillations in which the frequency of the driving force is equal to the natural frequency of the oscillator itself, and the amplitude of the oscillations is very large, and such oscillations are called as the resonant oscillations, and this phenomenon is what we know as the resonance. I hope this is clear. Is it? So let's look at the situation where we have a resonating air column, and we have one of the liquid over here, and what we are supposed to do is that we are having a tuning fork, and we vibrate the tuning fork, and we are just trying to arrange this air column such that resonance occurs. A tuning of the radio of receiver is based on the principle of resonance itself, that we arrange the frequency when you arrange the station, or when you try to tune in the station, you are having generally certain knobs. I'm talking about the mechanical radio receivers what we were having in the previous days, that whatever the dial, that generally black in color, that dial when you rotate, it will just try to match the frequency with the external frequency, and when they will try to match the external frequency and the natural frequency, you will receive the station. Yes, let's look at one very interesting case, is that why are the army troops, they are not allowed to march in steps while crossing a bridge? Because it is quite likely that the frequency of the footsteps may match with the natural frequency of the bridge, and if this happens due to the resonance, the bridge may pick up the large amplitude, and if it has been picked up a large amplitude and break, this is very dangerous for anyone. So they are not allowed to march when they passes through a bridge. I hope this is clear. Yes. Now let's look at certain quick questions. First, what is the length of the simple pendulum which ticks at a second? Yes, they are talking about the seconds pendulum. It is 1 meter. Great. Second, time period of a simple pendulum depends on Length of the pendulum, yes. Acceleration due to gravity, yes. Mass, no. So yes, this would be the correct answer. Next, the bob of a pendulum is made of a hollow brass sphere. What happens to the time period of pendulum if the bob is filled with water completely? When let's look at and understand the situation. It is the hollow one, and its center of gravity would be at this point. Now let's understand that we have filled up this with the water. Even after the filling of the water, the center of gravity remains the same. Yes, so effective length, what we call as the length, effective length remains the same, and as effective length of the pendulum remains the same, it would be the same. I hope this is clear. Was it clear? Was it? Great. So let's wind up the session over here. This was the forced oscillations and damped oscillations. So this was about the forced oscillation, then damped oscillations, as well as condition of resonance. Please go through the session very carefully. Yes, this is having an capability of two questions to be asked in the NEET or JEE examinations. Please go through this. This is very important topic. Thank you. Have a good day. Take care.